Point 3, geometric sequences and series. Objective, using a calculator with geometric sequences, find sums of geometric series. Remember that the geometric sequence can be written as an explicit expression, which relies on the first term and then multiplying by the number of ratios that you want to do to get to the term that you want to arrive at. Or you could do it in a recursive fashion where you multiply the previous term times the common ratio. All right, let's take a look at an example here. This sequence is being multiplied by a half each time, so we create this sequence. And what we would like to do is figure out the series, and the series would be, again, a sequence of partial sums. So the first sum, just adding this together right here, just the first term, the answer would be this. If you add the first two terms, this would be the second partial sum. If you add the first three terms, that would be the third partial sum. If you add the first four times, the fourth partial sum, and so on. So if you wanted to get to 10, adding up 10, that would be the 10th partial sum. Let's take a look at how we'll do that on our calculator with a recursive formula. So to get all of these values, what you're doing is taking the previous value and timesing by a half. And our first value is 1024, and then the second is 5012. So that's how we get the sequence. Now, to get the sum, what we want to do is we want to take the previous sum, which is this is the sum. We want to add the very next term. We're saying we want the sum. We want to add the very next term, and this is the answer we're going to arrive at for the second partial sum. Then we're going to take this sum, and we're going to add it to this 215. So this is the second partial sum. We're going to add it to 256, and we're going to arrive at this answer. So this is how we're doing it recursively. Let's go ahead and put it in our calculator so we get used to how we put this in. And so we go y equal, and you can see I've already put it in, but I forgot to put the times times by a half. So times by parentheses 1 divided by 2. Okay, and then the recursive would be, again, the previous sum plus the next term. So let's go ahead and I'll let you look at the window that I used. The numbers are going to be getting quite big, so I had to be really careful about my y min and my y max. And then we can go ahead and hit graph, and I'll go ahead and do trace. You can see that I'll go ahead and trace the sequence first, but they're going by half each time. Let me go back up, and this time I'm going to go to the series, which is the sum. So the sum is getting bigger and bigger and bigger, and pretty soon it looks like it's just like leveling off. It's not getting much bigger. It's kind of staying around a certain number there. Okay, so that's how we do it with a recursive formula. Let's take a look at doing it with an explicit formula. With an explicit formula, we're going to use the first term times the ratio to the n minus 1. And when we look at writing a formula for the sum of the sequence, we'll write it in this fashion. I'm going to jump over to this other one, which is probably starting to be your favorite. Here's the explicit form, but this is the way we use our math formula to do that. So let me go over here, y equals, and get rid of this and put it in an explicit form. 1024 parentheses 1 divided by 2 parentheses to the n minus 1. And those numbers still stay the same. We want to do an explicit formula here. We really don't have to do use of n. You can just do it with a summation here, but I just want you to compare the sequence with a series. So we go to math. I press 0 to get the format here, and we're going to go 1, 2, and because we want to keep graphing, and then we're going to do the formula, the sequence formula, and then parentheses 1 divided by 2 parentheses to the n minus 1. and then we'll go out here. Okay, and all of these numbers still stay the same, the first sum and then the second sum. And let's go ahead and graph, and we get that same graph. Let's take a look at the table so that you can see the table. Oops. There we go. There's our table. And let's start at 1. Let's see, start at 1. So I'm not sure why these numbers, I don't have n equaling 1. Okay, let's go up here. There we go. There we go. Okay, there we go. And there's our numbers on our sequence, and here's our numbers on our series that we're getting. Okay, if you don't want to see the graph, of course, you can just go on to your Calculate screen and figure out those numbers. And at this point, I'd like you to stop the screencast and see what you can do about solving this problem. Pause, please. And here's the answer. Notice that I showed you how to set it up in a recursive, and then I showed you how to use it in a explicit. Now, I didn't give the answers, but if you go ahead and graph that, I think you'll be fine. Now, here's another problem. Please pause and see what you can do. And here's the answer. The answer is not asking for a series, it's asking for a sequence. Notice that 3 every 2 minutes means 3 halves. The cell is growing by 3 halves every minute. So that's why I'm using the 3 halves and how I'm interpreting that problem. Let's go ahead and pause. See what you can do, set up the problem. And here's the answer. Again, here's another problem that's talking about just the sequence, not necessarily the series. And what I did is I didn't use the 70%, I used 30% because once 70% is moved, there's 30% of contaminants left. So I worked with a 0.3 to find out how many contaminants we have. And in the end, after 4 times, I found that the contaminants were 0.0081, which I subtracted from 1, and then that's how much had been removed, 0.9919, which represents 99.19%.